Hi everyone, how are you? I hope you are fine. So today's class, the recorded online class, we are gonna still look at infinite series. Okay, so if you haven't watched my videos on infinite series, please go to my YouTube channel AnyGB and search through all the topics on infinite series. Because there are several types of series: geometric series, telescoping series, alternating series, and there are also a few tests for the series. Okay, so divergent test, test for the geometric series, integral test. But today we're going to look at a test called ratio and root test. Okay, let's look into ratio test first. So this is one of the tests that you can use to determine whether the series converge or diverge as long as it satisfies the given condition. Okay, so let's look at the definition of this ratio test. So let's say you're given the series. Okay, this is a notation for series. Okay, remember series is a sum of a sequence. Okay, now what we do here, we define L. Okay, there is a constant L which we're going to equal to a number. Limit n approach infinity. Absolute. This is the series given at an plus 1 over an. Okay, so we have to remember this definition. Okay, the definition here is very important. So I think I want to write define here, not definition, but this should be define. I'm still going to write definition, my bad. Okay, define. Okay, so what happened here? Now this L, so if the value, this L should be a number, okay? If L is less than 1, then we say the series is absolutely convergent. Okay, when it's absolutely convergent, that means it's convergent. Okay, if L is greater than 1, and then we say the series is divergent. Okay, now there's another definition where when L equals to 1. Okay, so what we say that the series may be divergent, convergent, or absolutely convergent. Now, what this means? This means that you have to do another test because you cannot find the answer they're looking for when you get L equals to 1. So you just have to do some tests. Now, what does absolute convergent here means? The absolute convergent here means, this one means that a series is called absolutely convergent if the series of the absolute value is convergent. So anything in this absolute value, when you take the absolute value of a series, it must be convergent. Okay, so if you understand this definition, let's look at one example. Always you need example for you to understand. So the example here is given from my book. Okay, so let's say we're given this series from n equals to 1 to infinity, negative 10 to the power of n over 4 to n plus 1, n plus 1. Okay, so what we want to do here, the question is determine if the following series is convergent or divergent. Now, obviously, I didn't mention about absolute convergent, right? Okay, but you have to do, if you do the ratio test when L is less than 1, the series is absolute convergent. Okay, if you look at this type of series here, now you can see this negative 10 to the power of n. So you might think that why can't I use alternating series tests for this, right? But I'm going to show you that you can do this easily by using the ratio test. Okay, so don't forget to mention by the ratio test so that I know what test you're using. By the ratio test. Okay, so back to the ratio test. What is it? We have L equals to limit n approach infinity. We have to take the absolute of an plus 1 over an. Okay, this is right. So this is an. So this is an. Now what is an plus 1? Okay, so let's write it. An, if an equals to negative 10 to the power of n over 4 to n plus 1, n plus 1. If this is an, now obviously you need to find an plus 1. So when you see n, you have to plus 1. N plus 1, n becomes n plus 1. Now this is the part you have to be careful. 2 bracket n plus 1. N becomes n plus 1, and don't forget you have plus 1 still. And then here you have n plus 1 for n, and you have plus 1. Okay, be careful, just simplify this term here. Okay, what do you get? 4 to n plus 3. 4 to the power of 2n plus 3. Now this one will be n plus 2. Okay, now we gotta apply the definition where L equals to this definition. Limit n upon infinity. Divide an plus 1 over an. Okay, so we have L equals to limit n approach infinity. It's gonna be a very big division here. So this is an plus 1. So let me just write it like that first so that you don't make mistake. Over 4 to the power of 2n plus 3, n plus 2, and then divide by an, negative 10 to the power of n, over 4 to the power of 2n, n plus 1. Okay, so I'm just going to write it down. This is an plus 1 over this is an. Okay, and don't forget, I mean, obviously you're not forgetting, but there's an absolute sign here. Okay, so I always tell my student, if you have a division of a fraction like this, okay, so remember, if you have a division a over b over c over d, it simply means a over b times d over c. So this term here, you can change the order, the numerator and the denominator. Okay, so let's do that. Limit n approach infinity. So I have negative 10 to the power of n plus 1 over 4 to the power of 2n plus 3n plus 2 multiply. I'm going to swap this term here. So I have 4 to the power of 2n plus 1, n plus 1 over negative 10 to the power of n. Okay, maybe I can, yeah, I don't have to erase this. Okay, so this is what you get. Now what you do, simplify the term. Okay, you just gotta do simplify and find the value for L. Okay, so what we have here, so negative 10 to the power of n and negative 10 to the power of n cancels out. That leaves me with negative 10 to the power of 1. Okay, so I have negative 10. Okay, now this term will never cancels out this and this, right? So I will have n plus 1 over n plus 2. Now this term up here, 4 to the power of 2n, 4 to the power of 2n cancels out. Now I have 4 to the power of 1 and 4 to the power of 3. 4 to the power of 1 and 4 to the power of 3. I'm sure this can be simplified, right? So that will remain 4 to the power of 2 here. So limit n approach infinity, negative 10 to the power of n plus 1 over the term involving 1 and 1 remain 2. So I have 4 squared. Here you can write it 16 n plus 2. Okay, so I can take the constant out, which is negative 10 over 16. Sorry, is that negative? No, there won't be negative because I have absolute sign here. So be careful, student, you can do a mistake here. Because of the absolute sign, the negative term will become positive, and then limit n approach infinity, n plus 1 over n plus 2. Okay, now how do I apply limit here? Obviously, when n approach infinity, these terms cancels out. Or what you can do here, this is the divergent test, right? So what happened? You divide by your numerator, which is n over n plus 1 over n, n over n plus 2 over n. Divide by the highest power in your denominator. Your denominator is power 1, so divide everything by n to the power of 1. So this gives me 1. 1 approach n, when you apply limit, when n approach infinity, 1 over infinity. This approach 0, this approach 0. So I have, this is 1. So this limit here gives me 1. And there's not, it's a positive absolute value here. So you have a positive constant, a number which is L equals to 10 over 16. Now 10 over 16 is less than 1. Less than 1. So what we can say by the ratio test definition that I mentioned earlier on, if L is less than 1, the series is absolutely convergent. Therefore, it is convergent. Okay, so our summary here, the given series is absolutely convergent. Therefore, or you can say hence, will converge. Okay, that's Okay, now let's look at a few more examples. So we want to look at when the ratio tests converge, diverge, or also if it happens to be inconclusive. So you will get ratio tests inconclusive when L equals to 1. So let me just point it out earlier here. So the three cases, right? If L less than 1, it's absolutely convergent, therefore it's convergent. When L greater than 1, the series is divergent. If L equals to 1, so this part here, this will also mean the test is inconclusive. Okay, so you have to use different tests to determine whether the series converge or diverge. Okay, so let's back to one more example. So maybe I should start with an easy one and then difficult one, but it's okay. Okay, so let's look at the series here. We have n equals to 0 to infinity, 3n plus 2 over 5n power of 3 plus 1. Okay, so what we want to do here, we want to determine whether the series converge or diverge. So determine whether the given series is convergent or divergent. The best for convergence. So I think the best way to write this properly, determine whether the given series converges or diverges. Okay, so now what we want to do here, we want to solve this. Okay, so let's say what happened here if you were doing some other tests. Okay, so you can see that you can actually use comparison tests, limit comparison tests to compare this. Okay, or you could have do series tests. Okay, P series tests. So what do you do here? You compare this with summation 1 over n squared, right? But let's show by using ratio test. So by ratio test, so I need to find if this is my an, 3n plus 2 over 5n cubed plus 1. Now what is an plus 1? An plus 1 will be 3n plus 1 plus 2 over 5n plus 1 cubed plus 1. Okay, so now you can apply the limit. N approach infinity, the absolute value an plus 1 over an. Then what do you get? Equals to limit n approach infinity. So take this whole term here. You should have simplified. So let me just simplify this. You have 3n plus 3 plus 2. So 3n plus 5 over, what do you get? 3n. It's hard to simplify this thing here. I mean, you can, but I'm just going to leave it like that. Okay, now I'm going to write it down. 3n plus 5 over 5n plus 1 cubed plus 1. So this is just an here. This is an. Oh, sorry, an plus 1. Now we're going to divide by my an, which is this term. 3n plus 2 over 5n cubed plus 1. Now you can swap this part here, numerator and the denominator. So I have absolute 3n plus 1 over 5n plus 1 cubed plus 1 multiply with 5n cubed plus 1 over 3n plus 2. Okay, it's not that long anyway. Okay, so this is what you get. Now I have to simplify this term here. So what you can get here, there are a few terms cancels out. Right, so how to do this? So let me just write it down. You can see that 3n plus 5 with 5n cubed plus 1 over 5n plus 1 cubed plus 1, and then we have 3n plus 2. Okay, so you can see that we have terms involving n to the power of cube n. So you don't have to expand this, but you can expand, and then when you apply the limit, divide by the highest power in your denominator. But I can show you quickly here. If this is n to the power of cube, multiply with another n here. So what you will have n to the power of 4. Okay, just the variable term here. Okay, so the IS is n to the power of 4, and similarly this part here, 5n cube and n, you will have n to the power of 4. So if I have to divide each term by n to the power of 4, we will end up getting 1. So you'll get 1. That's what you will end up with. So you'll have n to the power of 4 divided by n to the power of 4, 1. So L equals to 1. Your ratio test is inconclusive because it cannot tell you whether it converge or diverge. So how to do this? You have to use limit comparison test. Okay, or comparison test. So I'm going to show you by the limit comparison test. Now, what's the limit comparison test? Say, apply the limit n approach infinity an over bn. You must get c. Now, c, if it's a positive, is a positive number. Therefore, we say the series converges. It don't have to be positive. Sorry. You have a finite number. Okay, if c is a finite number, you say it converges. If c you get infinite number, you say the series diverges. Okay, so you have to find what to compare with. So if this is your an, the given an is 3n plus 2 over 5n cubed plus 1. Now your bn, the suitable comparison for bn will be, this is a n here and n power 3 here. So it should be 1 over n squared. Okay, so you can compare with 1 over n squared. Now take the limit n approach infinity an 3n plus 2 over 5n cubed plus 1 over bn means multiply with n squared over 1. Okay, so I can see that this term cancels out by 1. I'll have 1 5n. Okay, so now what do you do? Gonna limit n approach infinity 3n plus 2 over 5n plus 1. So divide by the highest power in your denominator. That will give you limit n approach infinity 3n over n plus 2 over n over 5n over n plus 1 over n. So this term approach 0, not infinity. This term approach 0. This term approach 0. This term is 1, 1. So I have 3 over 5, which is a finite number. Therefore, the series, the given series n equals to 0 to infinity 3n plus 2 over 5n cubed plus 1 converges by the limit comparison test. Okay, it's not absolutely convergent because by the ratio test, the limit is inconclusive. The limit does not, we don't know whether it converge or diverge. Okay, so it's not absolutely convergent. Now, there is an absolutely convergent test if you want to determine whether the series is absolutely convergent or not. Because if a series converges, it does not mean it's absolutely convergent. In order to determine whether the series is absolutely convergent, you need to apply the absolutely convergent test. So we can check. Okay, now let's try. By the absolutely convergent test. Okay, so nothing gonna change here. There's no negative sign, right? There's no negative sign here. So even you apply the limit, the absolute value to this term here, the given term here, 3n plus 2, 5n cubed plus 1, it's not going to change. This is never going to be absolutely convergent, okay? The series is not absolutely convergent. Okay, so what we can say that the given series is convergent but not absolutely convergent. Okay, so this is when if you happens to get a ratio test inconclusive, or you can say that if the ratio tests fail to show you whether it converge or diverge. Okay, so let's look at another example. Okay, so let's look at one more example here. So given the series sum n equals to 1 to infinity 2 to the power of n over n to the power of 100. Now again, the question wants you to determine if the given series, or we can say that determine if the given series is maybe I want to say absolutely convergent. Convergent, divergent, or divergent. Okay, determine if the given series is absolutely convergent, or divergent. So normally if you're given something called absolutely convergent here, So what you do, you could do the absolutely convergent test, but that would not tell you anything whether the series converge. Okay, so the best way is to do the ratio test. Okay, so by the ratio test, similarly what we have done before, now actually if you do the convergent test, I mean the absolutely, to determine the absolutely convergent, you can do the absolutely convergent test, right? That will obviously tell whether the series converge. Okay, but I want to show you by using the ratio test. So we have an equals to 2 to the power of n over n to the power of 100, and an plus 1 equals to 2 to the power of n plus 1 over n plus 1 to the power of 100. Okay, now we can say L equals to limit n approach infinity an plus 1 over an. That gives you limit n approach infinity. Now I have this term here for an plus 1. N plus 1 power of 100 divide by an. So I'm just going to swap the denominator with my numerator. Okay, so simplifying, what I can simplify, the only thing I can simplify is this term here. So I have 2 to the power of n. I take out the 2 out, or just write it down first. So I have 2 times n power 100 and n plus 1 power 100. So I can write it n over n plus 1 to the power of 100. Okay, please be careful because you cannot cancel the term from your numerator with your denominator, okay, because you have an addition here, it's not multiplication. Okay, now simplifying this to, what can I do here? How can I simplify this term here? So I have applying the limit for this term here. So this term here, how do you apply the limit? So divide by the highest power in your numerator. Don't forget the absolute value sign. So that will gives me 1. This is 0. So I 1 to the power of 100. So L equals to 2 times 1 to the power of 100, which is 2. Okay, now this 2 is greater than 1. Therefore, we can say that the series summation n equals to 1 to infinity 2 to the power of n over n to the power of 100 diverges by the ratio test. Okay, so you get a value for the L constant. If it's greater than 1, we can say that the series diverges. Okay, that's some of the example by using ratio test. Now I'm going to give you homework that you need to submit to me. Okay, so there are 2 questions that I want to give you. Question 1 is the series summation n equals to 0 to infinity n factorial over 6 to the power of n. And number 2 is this one. Summation n equals to 2, sorry, not 1, n equals to 2 to infinity 1 over n ln n. Okay, so what I want you to do is determine whether the given series is convergent, or divergent. Okay, so that's you gotta do. Now, I really want you to use ratio tests. Okay, use ratio tests to determine whether the series converge, diverge. Now, when you use ratio tests, you can also say the series can be absolutely convergent. Okay, if the series is absolutely convergent, the series is convergent throughout. Okay, that's all for examples using ratio tests. Now, in my next video, I'm going to show you there's another test that you can use to determine whether the series converge or diverge by using root tests. So let's watch the next video. Bye for now.